Our next speaker is going to be Sreejata. He is going to be talking about an exponential separation between powers of regular and unrestricted resolution over parities.
What is the right arrow?
Pull it up.
Click on the screen. Even this is not working. So just click on the screen. Okay, so thank you. This is joint work with Bhattacharya and Pavel Boda, who is not here. This was presented in CPC 2024. So I will first start the talk by talking about resolution. And this is the most basic proof system. So what's a proof system? Let's say you have an unsatisfiable CNF and you want to certify that this CNF is unsatisfiable. Now, how do you do that? So initially you have some clauses C1 to Cn and observe the following. If you have two clauses A or X and B or not X, then combine these two clauses combined imply A or B. So one way to certify that this CNF is unsatisfiable is start from the initial set of clauses and repeatedly derive new clauses using this derivation rule. And if you can derive the empty clause, then this sequence of derivations is a certificate that P is not satisfiable. And such a certificate is called the resolution reputation. Now some basic questions. Can we expect that so first of all, every unsatisfiable CNF has a resolution reputation. This is easy to do. Now, can we expect that every CNF has a small name resolution reputation? The answer is no, because that would imply NP equals to co-NP and the world would get destroyed. So, okay, at least, okay, now that we don't expect such things to exist, can we explicitly construct a CNF that does not have any small resolution reputations? This was first done by Haken. I don't know if it's the first one, but Haken showed that, okay, if you encode pigeonhole principle in a CNF, then that CNF will not have any polynomial size resolution reputation. Now, okay, this is just one proof system. Now, what about other proof systems? Like Yogesh just said, there are many stronger proof systems than resolution that people think about. So, for every circuit class, there is a corresponding proof system. Right? Each proof line is a circuit from that circuit class. I'm not going to go into the details, but if the circuit class is C, then the corresponding proof system is called C. So resolution would correspond to clause Frege, and the hardest thing is extended Frege, which corresponds to P by 1. So, and again, people try proving lower bounds against increasingly stronger proof systems. And again, as Yogesh has mentioned, in this direction, we have lower bounds for AC0 Frege, but we don't have lower bound for AC02 Frege. And the hope is that 1 million years from now, we will prove a lower bound against some very strong proof system that would imply NP not equal to NP, but that is very far away. So we just try to analyze weak systems. So the frontier lies between AC0 Frege and AC02 Frege. So this is unlike circuit complexity, again, as you mentioned, because we don't have an analog for Raz-Smolensky in proof complexity. So the issue is that we not understand the power of parity inferences when it comes to refuting CNFs. So, to understand this situation better, so let's see what we have. We have lower bounds for resolution. We have lower bounds for AC0 Frege. But as soon as we add mod 2 to AC0, we don't have lower bounds against it. So to understand this situation better, Itsykson and Sokolov suggested the following. Instead of adding mod 2 to AC0, let's add mod 2 to resolution. So I'll define this proof system. They define the proof system called ResLin. So you basically add the power of mod 2 counting to resolution. I'll explain this later. But so currently the frontier is here. So we don't have lower bounds for this new proof system, ResLin. And proving lower bounds again, this is a major open problem. So what is ResLin? So in resolution, every proof line was a clause. Here, every proof line is a conjunction of linear forms. So it's saying that at least, do you have a laser pointer? No. Okay. So it's saying that, so every line looks like this. You have m equations over f2, and it's saying that at least one of these m equations is satisfied. Equivalently, its negation is an affine space. Now, what are the inference rules? Here we have two inference rules. One is, so such a thing is called a linear cross. And we have two inference rules. One is if a linear cross C1 semantically implies another linear cross C2, we can derive C2 from C1. And the other is just like resolution. So if we have A or some equation and B or the opposite of that equation, you can derive A or B. So this is clearly a sound and complete proof system.
Each equation itself is an OR of each line itself is an OR of equation.
Yes. So in normal resolution, each line was a OR of equations where each equation is like xi equals to b.
There was like coordinate
Equations here. Here I am allowing general equations. So okay. So this is a sound and complete proof system. And
this is different from usual. There's another thing called ResLin in which each line is just an equation and you're just asking if all the equations are simultaneously. This is can be checked using Gaussian elimination.
yeah, this is not.
This is not that.
This is not.
Each line is a conjunction
OR of equations. Yes.
or a disjunction of equation.
Yeah. Okay, so why is ResLin more powerful than resolution? It's because this weakening axiom. So by the way, you can do weakening in resolution too, but that does not add any power. Here it adds a lot of power. Why? Here's an example. Okay, I mentioned this 2 minutes ago. Yeah, so here are some things you can do in ResLin but not in resolution. Let's check any linear clause. Now look at its negation. This is an affine space. Now you can write this affine space in any other basis, as in you can write these equations in any other basis. And if you negate it again, you get another expression for the same linear clause. So you can write the linear clause in many different ways by using different bases. And by choosing different bases, you can expect that using this new expression, you can do more resolution steps. And then you can again express it in another basis and do some more resolution steps.
But x1, x2, xn automatically is a canonical basis, right? So your new basis.
No. I'm saying write these equations in any other basis. As in, this is the set of defining equations. This is not the coordinate basis. This is some general basis. And you can express it in any other basis. Here, AI is not the standard basis vector. So I'm saying the inner product of AI comma x, this defines an equation. So you can write the AIs in any other basis in the equation space, and you can express it in a different way. So you have many different representations of the same linear cross. I hope this is clear. And using different representations, you can resolve with different other crosses. So this gives a lot of power. And indeed, it is known that ResLin can be exponentially more powerful than resolution. And one example is the citing contradiction. Okay, so I'll now talk a bit more about resolution reputations. So let's consider any resolution reputation of an unsatisfiable CNF. Now, for any unsatisfiable CNF, you can define a search problem. Now, what is a search problem for the CNF? It says given an input x, output a clause such that x does not satisfy this clause. And note that if you look at the resolution reputation top down, it automatically becomes a branching program for the search problem. Here the sinks are labeled with the corresponding clauses. And if a node is derived by resolving a variable from two other nodes, then from this node you have two edges leading to those two nodes. And as an example, here is the path followed by the input 0, 1, 1 on this branching program. So how is this path defined? You start from the root, that is the empty clause. Now look, there are two edges going from the root, x1 and not x1. You look at which side the input falsifies. So x1 is 0, which means it falsifies the right edge.
So you go to not x1. Now you branch on x3. So look at which side this input falsifies. X3 is 1, so it falsifies not x3. So you go to this slip and you have this answer. Indeed, note that this input falsifies this clause. So in general, you can, this is a tree, but the general figure will be a branching program. If you just, yes? No, I am defining the path to this way that,
No, I think that there is a mistake, otherwise this one or this is said. Yeah.
I think in the bottom time. So the first two are x1 and the next two are not x1.
this is,
In the clause.
no, x1 is 0.
Or x.
Yeah, okay, this is a mistake. Should have gone in this side.
This should
You
be.
know,
not
the labels got reversed. Sorry, yes.
Oh.
Yeah,
Okay.
the labels got it up, yeah. It should be x1 or not x3 here. So, okay, so that's naturally, if you look at, sorry for the mistake, if you look at any resolution reputation,
This 350 now is going from the bottom of this.
if you, do- yeah,
Each node is like a resolution of. the
yes,
tree.
yes, but if you just look at it top down, it becomes a branching program. Yes.
The two clauses on the right, when you resolve, you get x1, you don't get not.
Yeah, so it should be not x1 or x3 or not x1 of
The
the.
two clauses.
Oh, no. For some reason, the not did not come in the latex. So,
It is already resolved in your head, right?
that's right. No, I think I have said AEG, I wrote something else and it did not come. Well, yes, sorry. So, this would be not x1 on both sides. Yeah.
Is this your AEC slides or?
Yes, I'm.
We are better audience than CCC.
Yeah, sure, yeah. So, okay, so again, some basic properties of this branching program. Note that the negation of each clause is a queue. So, to each node, you label the corresponding queue. And the main observation is that if the path of x visits a node, then x lies in the corresponding queue. Okay, so yeah, so if the path of x visits a node, then x lies in that queue. So now if the associated branching program of a resolution reputation is read once, then we call the reputation read one regular resolution. In other words, in any chain of resolutions, a variable is resolved at most once. The following conjecture was proposed many years ago that regular resolution is as powerful as resolution up to polynomial factors. And this was disproven recently by Aleknovich, Johansson, Peterson, and Urquhart. So they gave a CNF which has a small resolution reputation, but any regular reputation requires exponential size. And regular resolutions have many nice properties which make them simpler to construct and analyze. Another important thing is that all SAT solvers actually output a regular resolution reputation. This is why they are a very highly studied object. So, okay. Now, similarly, if you look at a ResLin reputation, if you look at it bottom down, it becomes a linear branching program. So here at each node, you query a linear form and you go to the side which is falsified. Now again, now each node is labeled with a linear clause. And if you so the negation of a linear clause is an affine space. So label each node by the corresponding affine space. And again, we have the observation that if the path of x visits a node, then x lies in the corresponding affine space. Now, yeah, so now since people were not able to prove lower bounds for ResLin, Griyasnov, Putlak and Talebanford proposed the following. Let's define a notion of a regular ResLin reputation and first try to prove lower bounds against this. So there are many ways you can define what is a regular linear branching program. The definition we will stick to in this talk is the following. So let's say, so I'm going to define what is a regular linear branching program. So let's say we have a node U and its children are V0 and V1. Now let post of V0 be the span of all the linear forms queried in a descendant of V0. Then we require and let L be the linear form queried at U. Then we require that L is not in the span of post of V0. In other words, in any subtag of V0, look at all the linear forms that we have derived. L does not lie in their span. And the same holds for V1. So this is a notion of regularity, as in whatever you have derived in the bottom, you are not using in the top. So Griyasnov et al. Proposed the following open problem. Okay, and the regular ResLin reputation is simply a reputation whose branching program is regular. So Griyasnov et al. Asked the following open problem: prove a super-polynomial lower bound against regular ResLin, and then hope that if you are lucky enough, it can also extend to a lower bound against unrestricted ResLin. So this problem was solved in STOP 2024 by Efremenko, Garlík and Itsykson. They gave a form. Okay, so they moved the frontier from bottom regular ResLin to ResLin, and but the formula they used to prove their lower bound was the binary pigeonhole principle, and it is conjectured that this formula is hard even for unrestricted ResLin. So it was still not clear. Yeah. Okay, I'll define it after the dog because there is not enough time. It's just a different way to encode it. So, but this formula is conjectured to be hard even for unrestricted ResLin, and it remained unclear whether or not unrestricted ResLin is as powerful as regular ResLin. And in our paper, we answered this question. Unrestricted ResLin is actually exponentially more powerful than regular ResLin. So there exists a CNF which has a small, even normal resolution reputation, but any regular ResLin reputation requires exponential size. So I'm going to give a how much time do I have? So I'm going to give an outline of the proof of Efremenko et al. And then I will give an outline of why we modify it. So how do Efremenko et al. Prove their lower bound? So I'm not going to describe what CNF they use. I'm just going to say what properties of the CNF they use. So let psi be the CNF against which we are trying to prove a lower bound, and let P be a regular ResLin reputation of C. Now again we can view this reputation as a linear branching program for the search problem, and for an input Z, let NTZ be the node visited by the path of Z after T steps. So so in the first step of the proof is the following. So that if we uniformly sample an input,
What is that?
Z is any input to the search problem, and NTZ is the node visited by Z after T steps in the branch program.
What is X equals?
Yes, but now I'm in the lifted space. Yeah. Yeah, so so we'll choose T appropriately. So the first step of the proof is the following. They show that if you have any decision parity decision tree of height at most say n power 1 by 3, and if which claims to solve the search problem, and if you uniformly at random give an input to this parity decision tree, with high probability the parity decision tree will fail. In other words, the parity decision tree complexity of the search problem under the uniform distribution is high. By high, I mean around poly n power 1 by 3. And using this, and using the regularity property of the ResLin reputation, they show that if you uniformly at random sample a input Z and look at where Z lands up after T steps, this node is NTZ, then the codimension of this affine space is at least omega T. Okay, and now we are done. Because note that this is an affine space which has large codimension, and Z actually lies in this affine space. However, if the codimension of an affine space is large, then probability that a uniformly at random input lies in this affine space is exponentially small in the codimension. This is just simple linear algebra. And that means that there are exponentially many nodes. Because we know that with high probability, as we sample Z, we'll end up with a high codimension node. But for any fixed high codimension node, only exponentially small fraction of inputs can land in that node. Therefore, there must be exponentially many nodes. And this is the proof of their lower bound. Now, we try to prove a separation between ResLin and bottom regular ResLin. And if you want to carry this program, at first we need to find a CNF which is easy for ResLin, but whose search problem is hard for parity decision trees, and we are not able to find any such formulas. So what can we do? Okay, we want a formula which is hard for the uniform distribution, and here's the workaround. Why do we need to consider the uniform distribution? It is simply because of the following property that if codimension of an affine space is large, then probability that Z lies in that affine space is exponentially small. And this is the only property of uniform distribution that they use. So can we think of other large class of distributions for which such a property holds? If we can, then we are done, because we can consider the hardness of the search problem with respect to those distributions. And our key observation is that indeed, yeah, so can this property be true for other distributions as well? Our key observation is that if we choose a gadget appropriately, this property is true for any lifted distribution. So what is a lifted distribution? So let's say we have a base space which has n variables, and we have a lifting gadget. Now the lifted space consists of, so the lifting gadget is defined on b bits. Now the lifted space consists of n times b many variables. We have b variables for each initial variable. Okay, so what is and this defines a lifting map from the lifted space to the unlifted space. I think this is natural. So what is a lifted distribution? So this is 0, 1 power n. Yeah, so so what is the lifted distribution? We simply choose any distribution on the base space and choose a uniformly random pre-image. Any such distribution I am calling a lifted distribution. And our main observation is that if we choose the gadget to be inner product on around order log n bits, then the property that we are talking of for uniform distribution actually holds for any lifted distribution. So you choose any distribution on the base space, sample according to that distribution, take a uniformly random lift, then the probability that it lies in A is exponentially small in the codimension of A. So what is the advantage? Now we do not need to prove the hardness of the search problem under the uniform distribution. We just need to prove the hardness of the search problem under lifted distribution. Okay, I'm going to skip this. So okay, we'll choose a lifted distribution and we'll prove a hardness for the search problem. Now we have to prove the hardness against parity decision trees, and this seems hard to analyze. So how do we do this? Here we need another idea. Yeah, so we need that the parity decision tree complexity of the search problem is high with respect to this distribution. And to do this, we need another idea. The idea is that we take the base distribution to be a distribution for which the search problem for normal decision trees is hard. And normal decision trees are easier to analyze. Such a distribution is not hard to construct. And given this distribution, we lift this. And we can use query to communication lifting results. Note that if Alice has X and Bob has Y, then any parity query can be done. They can do any parity query with 1 bit of communication. So we can use query to communication lifting theorems to show that if the base distribution is hard for normal decision trees, then the lifted distribution is hard for parity decision trees. And it's known that inner product with order log n gadget size supports query to communication lifting. And finally, we need to show that, okay, if the parity decision tree complexity under this distribution is high, then with high probability it visits a high codimension node. And to do this, this is the technical step. I'm going to ignore the details, but we have to combine ideas from 3 previous papers, and luckily everything works out. So here is our proof overview. We take G to be the inner product gadget on order log n bits. We construct a distribution mu on the base variables such that the query complexity of the search problem under that distribution is high. Then using query to communication lifting theorems, we show that the parity decision tree complexity of the search problem on the lifted space is high. And then using some technical things, we show that, okay, if we sample Z from this lifted distribution, with high probability, it lands at a node whose codimension is at least T. T is like n power 1 by 6 here. And this is our observation that if the codimension of an affine space is at least R, then the probability mass of this affine space under any lifted distribution is exponentially small in R. So again, by the same bottleneck argument, we have that therefore there are exponentially many nodes in the linear branching program. And it turns out the upper bound is easy. How much time do I have? Yeah, the upper bound is easy, and I'm going to skip that. So, and these are some open problems. You can leave them. So, any questions?
Right. Right. It's all the problem.
So, thank you. Any questions?
Any questions?
Yeah, I think the decision tree was that there was a typo in the LaTeX and the negative sign did not compile.
But the
So,
something.
what is the open problem?
Is that what?
Oh, sorry, against random CNFs for bottom regularity. This is how the thesis is like that. I fixed it in the. Yeah, yes. I think they uploaded the previous version.
Point the term rest parity for this stuff.
It was introduced. So first, Raz and Tzamaret defined an extension of resolution, but it was not mod 2. It was over equations over Z. Then Itsykson and Sokolov said let's do it mod 2. And then one of them defined this. Yeah, I don't remember very much.
No, they sound defining the class. This particular notation things are bad. So there's another class called ResLin, which is just equations and you're taking a parity of each line is an equation, you're taking parity.
No, I think ResLin and this is the same.
That's also called ResLin. I thought ResLin is. Okay, I've seen ResLin and Jacobson and Nelly's papers which talks in which each line is a linear equation and resolution step is taking parity of sum of two linear equations.
So how can each line be a linear equation? That sounds very.
You just asking the set of series stuff.
Then that's just like a system of linear
It's
equations.
just a system of linear,
Yeah.
but you can talk about only operations you can do. Adding them and you can ask them how long does the system take to.
Then there is just the Gaussian.
It is just Gaussian,
Yeah.
but this is studied in the, and I've used the only reason I'm bringing it up is papers which refer to this system also as ResLin.
Yeah, okay, so the papers I will refer to this system as basically.
Two open problems.
Okay, so any more questions? Yeah, this should be random CNFs. So this is not the CNF, right?
Then there is another mistake. The whole slide has. Oh, big things are first.
No, this is right.
But it's more than that.
Okay, let's time this.